Hey, hey, it's Dr. J. I'm back with another application of the derivative. Um, in my first attempt at this video, I had some technical difficulties, so I appreciate your patience. I'm sure you all have been waiting on the edge of your seat for this video to premiere. And so here it is, Elasticity of Demand. So what is this about? We start with a demand function. As a function of price. All right, and so the notation that I've been using for the demand as a function of price is x of p. Now, when you are working with this function, you input a price and then it outputs a demand. You could write it like this, and I may have done that, and I may do that again in the future, but to me, especially in this lecture, this looks funny, right? Just to say x of p equals x. And so I'm going to introduce a new letter, Q, for quantity. So the output is a quantity. It means the same thing as x. When we're analyzing the values, it tells you how many of that object or item, or how many units, what the quantity of that demand is for a given price. Okay. I won't actually give you a specific equation yet. I first want to start with the definition. So the definition, elasticity is equal to E. It's the symbol we use for elasticity. And it is the absolute value of the derivative of Q with respect to P, so dQ dP. When you're taking the derivative, you can think of Q as being like the Y variable. It's the vertical. And you can think of P as being the X. And I know that sometimes can be confusing because I'm using the letter X as the name of the demand function, but you'll get it when I start doing some examples. Multiplied by the quotient P over Q. All right. Now, before I actually do anything, let's just interpret what this means. The first thing I'll mention is the absolute value is there because generally demand function is generally negative. And this is the rate of change, right? The derivative measures the rate of change. And so what we do is we use the absolute value bars to ensure that the result is positive. So that's the only reason why we need them. So what this does is this ensures, is it ensure or ensure? All my English majors out there, ensure a positive result. All right. It's just part of the definition. We like to measure elasticity using only a positive number. All right. And so when this quotient comes out to be negative, the absolute value will change it to positive automatically. And then what is the P over Q? The P over Q is the ratio of price to quantity. So it gives us this ratio of how the price and the quantity are related, right? And so when we calculate this value, we get a positive number. Now notice that if the rate of change is inverse or reciprocal of this ratio, that this result will come out to be 1. If E is equal to 1, then this ratio is, well, it actually comes out to be negative 1, but when you take the absolute value, you get positive 1, right? It means that a 1% change in price results in exactly 1% change in demand. And so we call that unitary. So for every 1% that we change the price, it results in exactly a 1% change in demand. And so that's why the ratios are set up this way. You can see DQ is on top and then Q is on the bottom. So if these are changing at the same rate, then these will cancel out and everything will become 1 or -1. And then when you take the absolute value, you get an elasticity of 1. That's sort of our goal. All right. That's it's not always going to happen, but that's our goal in optimizing the price as it relates to demand. Okay. But it's not always going to be 1. There are 2 other options. It could be less than 1 or it could be greater than 1. Let's get into the weeds on that. So let's start with just a general, here's the idea. I won't actually do any specific calculation yet, but let me just kind of give you the idea. Suppose at a price, an item, when priced at $5 per unit, the demand is 54 units. I don't know if you could read that. 54 units or 54 items or however you want to say it. So suppose that. All right. I'll reproduce this formula in just a minute. So what that means is that you have price is like your X, Q is like your Y, and then you have some point here, 54 units, that's the quantity, and then the price is $5, and that gives us a point here. Then, if we increase the price to say $9, well, what do you think is going to happen? Generally, price and demand have a negative slope, right? Although it's not always a line. In this sort of, to get the idea, I'll draw it as a line. It could be curved. If we increase the price to say $9, as you can imagine, the demand goes down. It decreases to, and again, I'm just making these numbers up just to kind of give you the idea. The demand, say, decreases to, say, 30 units. And again, I'm not being super precise about the coordinates. This graph is not to scale, but it hopefully shows you the idea. So what you can see is that the slope, dq dp, is negative. All right, that's going to happen every time. So whenever you take the slope of a demand function, price demand function, you're going to get a negative slope. Now, what is that slope? Because this is a line, we don't need to use calculus, right? Although I'm still going to use the calculus notation. It's just a fancy way of saying rise over run, right? And so you can calculate it very easily. Here, let me erase the word negative. You'll see that it's negative in a minute. All right, it would be 54 minus 30. I'm going back to old school algebra. And then now if you do 54 minus 30, because 54 corresponds to the 5, you have to do 5 minus 9. Now, although I did make these numbers up, I made them up to give you the idea. so I made them very nice. So that's going to be 24 over -4. And so this dq dp is going to be -6. Right? It's just a fancy way of saying slope. It's the calculus way to say slope. All right, so we need to have that first, right? We have to have the rate of change. And in a line, it's very easy. It's just the slope. For more complicated functions, you know, if they're curved, then we would use some of the techniques that we've learned in the last few lectures about taking derivatives. So now we have the slope. All right, so now we can find the elasticity. Now, the elasticity is based on the price and the quantity, the associated quantity. All right, so let's go ahead and do it. So we've got elasticity is the absolute value of dq dp times p over q. All right, and so let's choose this price. Let's choose that price there. So for p equals 5, our q is 54. And then the slope is going to be -6 for no matter what point we use on this particular graph. So for the dp dq, we have -6. That's our slope, times the price, which is 5, over the quantity, which is 54. Again, the slope is technically -6 over 1, although we just write it as -6. So that would be the absolute value of -30 over 54. You could just ignore the negative sign because it's going to turn positive. And you're going to get 0.5555555. I'm going to have you round this to 2 decimal places. So we would say the elasticity at this point is 0.56. All right. Now, this is, not only is this going to be, this is calculus, although this particular calculation is pretty mild in the calculus part of it, but mainly I want to focus on the interpretation, right? There's a lot of interpretation going on here. All right. So there are 3 possibilities. E could be less than 1. Yeah, we call that inelastic. All right. And what it means is the price is too low. So what we should do is we should raise the price, or increased. It's called inelastic. The price is too low. It's less than 1. And what we should do is we should raise the price, decrease the demand, all right, and this will increase the revenue. Now that's the weird part. Why does it increase the revenue? Well, I have to draw you another picture, but I want to keep this picture here. So I will explain in just a minute. So this needs confirmation, I guess. Or maybe it doesn't. Maybe it makes sense to you. If you decrease the demand, how does that increase the revenue, right? Because you're going to be selling less of these things. It needs confirmation, and I'm going to have to show you a different graph, but clearly I don't want to ruin this beautiful graph that I already have here. So right now I'm just focusing on the terminology. So if E is less than 1, we call it inelastic. The price should be increased, and then that will decrease demand. Okay. Now, how does it decrease the demand? Well, for every 1% increase in price, demand will decrease by 0.5%. Whatever this elasticity comes out to be. Don't do any kind of moving of the decimals. This is already in percent form, so it's 0.56%. I know in a basic arithmetic, when you're learning percents, you learn some tricks about moving the decimal from left to right. That's already been baked into this formula. So if you get a decimal, 0.56, that means 0.56%. The percent is already implied in here. Okay. I don't want to get too deep into the weeds on how that works. Just trust me. All right. It is what it is. All right. And as we do some examples, plug in some actual numbers, you'll hopefully get the feel for it before this lecture is over. All right. So that's the first one. Inelastic. All right. Write that one down. If you want, we can keep tabs on all of this. So E less than 1. We'll just write down the keyword inelastic. Now, if I had a bigger board, if I was in a classroom, I'd probably move over to another spot, but I'm going to have to erase all this, okay? So we'll come back to this. We'll do a different one. Let's do the other price, $9. So now let's focus on this point here, $9. Again, I don't have to do the slope again. The slope is still -6 over 1, or simply -6, times P over Q, so 9 over 30. Yeah, the quantity for $9 is 30. That gives me -54 over 30. $54 divided by 30. You can just ignore the negative. Oh, that one's nice. That comes out to exactly 1.8. No rounding necessary. And so right here, our elasticity is 1.8. Well, what does that mean? We call that elastic. E is greater than 1. It's called elastic. So let's put that over here. E greater than 1, elastic. All right. So what does that mean? Well, it means that we should lower the price. Yeah, we want our goal is to get to here, to get to somewhere in the middle. Although it's not always exactly in the middle, as we'll find out. But in this drawing, I will have it be right in the middle, just to kind of get the idea. This is a very simple, sort of prefabricated example here. All right. So we should decrease the price, increase the demand, and that will increase revenue. All right. Now, again, I'll put a little question mark here. We'll have to verify that when I'm done with this space here, and I can show you the idea. Okay. In terms of the percentages, for this one, for 1.8, for every 1% decrease in price, demand will increase by 1.8%. That's the result of being elastic. Which, you think about it, that's pretty good. That's almost double. 1.8 is almost 2, right? And so I'm decreasing the price only by 1%. And you think of money, 1% is a penny for every dollar in price, right? So if something was $20, then you would decrease the price by 20 cents, right? Just lower it by 20 cents. And then the demand will go up by 1.8%, right? And then remember, demand is not measured in dollars, it's measured in units, quantity. So that would cause this 30 to go up, right? Just by lowering the price. Oh, why did I say $20? I might have just stuck with $9, right? $9, sorry, scratch that. $20 is way off the board here. $9. So if I decrease the price 9 cents, right? That's all I got to do, 9 cents. So I make you feel like you're getting a deal, right? $8.91. So I decrease the price by 9 cents. Then the demand will go up by 1.8%. Just for fun, since I'm here, 1.8% is not much. Oh, yeah. It's not even a whole unit. All right, so it goes up to 30.5, almost 31. I guess if you rounded that would be 31. But remember, it's for every 1%, so it doesn't mean that you only have to change the price by 1%. That's just giving you a marker for every penny that you change the price, you decrease the price, that the demand will go up by that much. Clearly for this one, if you wanted it to go up to the next unit, which would be 31, it looks like we would have to lower it by 2%, right? But again, that's the idea. This is just the vocabulary here. Okay. All right, and then finally, let's take a price in the middle. Now, in this example, if you can, it's not really an example yet. It's not official. This is just kind of getting the terminology out. Kind of get it all out there now, and then I'll repeat it throughout the lesson today. So I bet I should probably finish this up. Let's just go right in the middle, $7. All right, and see what happens. I've prefabricated this example so that it comes out very nice. So let's do $7, right? And let's see what the demand is. Now, I didn't give you an equation, so you're just going to have to trust me. The demand is 42 for this one. 42 units, which happens to be right in the middle, because it's a line. So I guess you could say if the demand function is defined by a line, then you will have nice symmetry here. Things will be right in the middle. All right. So notice this is less than 1. This is greater than 1. I've cooked up this example in such a way that it comes out to be exactly 1. So again, the slope is the same, -6. The price is $7. The quantity is 42. You can see how I pre-cooked this one, so it'll come out nicely. And so this is what I meant earlier when I said that these ratios will exactly cancel each other out. And this is just 1. That's the absolute value of -1, which is just 1. Yay, that was our goal. I made this one super easy, and I didn't even have to give you an equation, just kind of give you the terminology. All right, so E is 1. This is called unitary. This one has lots of different terms, or unit elastic. Same thing. Unitary is the quick way to say it, or unit elastic, or the long way to say it is the demand is of unit elasticity. I'm just going to say unitary. But I might sometimes say unit elastic. Well, what does that mean? That means keep the prices unchanged. All right. Keep the price unchanged. It's perfect. Right? That is the perfect price. This is what we call optimal. It's the optimal price. Yeah, unit elasticity. It's the best price. All right. Revenue is already maximized. Or it's maximal. We've already reached the maximum revenue. Okay. Now, I should mention that when you have unit elasticity, you could still change the price, right? I don't know why you would, but I mean, maybe you're trying to, clear the shelves, right? You're having a sale, right? You're just like, you know what? I want to get rid of all these old products and I just don't care about the revenue being maximal anymore. I'm willing to sacrifice some of my revenue in order to clear the shelves, right? A going out of business sale or a end of the year sale or something like that. You could actually change the price. I don't know why you would. There'd have to be a reason. And here's the result of unit elasticity. For every 1% change, it doesn't matter whether you increase it or decrease it at this point, right? So you could raise the price or you could lower the price. Although I guess if you're trying to clear the shelves, you would probably lower it. But I'll just say change. Yeah. In price, demand will change by 1%. Exactly. So it's really cool. If I change the price by 1%, well, then the demand changes by 1%, right? If I decrease the price by 1%, lower the price, the demand will go up by 1%. Now I will lose some revenue, but again, you would be doing that intentionally. Generally speaking, when I ask about unit elasticity, I just tell you to keep the price unchanged. But if you're in business, if this is your business, you certainly are allowed to still change the price if you like. I don't know if you have some logic behind that. Okay. So that's the summary of the terminology and the consequences of elasticity. So before I do my first legitimate, calculus example, let's talk about why or how does changing the price affect revenue? Well, it's a different graph, which if I had a larger board, I would write them. Sorry, that's not Q anymore. That's R for revenue and price. Well, revenue is price times demand, or price times quantity. I've written it both ways, right? Price times Q or price times X of P. These mean the same thing. I like this one today. This is the one I'm going to be using today. All right. This one also works, and you'll see some examples where I use that. The equation looks a little more complicated when you use the function notation. This notation is super simple, right? Super simple. All right. So how does that work? Well, clearly revenue starts at 0 because if you sell nothing, right, the price is 0, the revenue is 0, right? If the price was $5, so say R5, I'm not using function notation, but I'm just going to put it here. It would be $5. And if you remember the quantity was 54, you would have to recall that. If you plugged in $5, you would get out 54. I already erased the old graph, but you can hopefully recall that. And then your revenue would be, what is that? 270? I'm feeling pretty confident. Or is it 275? 54 times 5, 270, yeah. All right, so you have, 270. And then over here, the price was $9. What was the quantity for $9? 30. Oh, look at that. It comes out to still be 270. So these two were equal. Yeah. So revenue is going like this. Right. Now, I don't know where it hits the ground. I don't really care. I would not want to sell it for that price. So I kind of just like to draw it like this. Right. Yeah, it's a parabola. It eventually will hit the axis, but the value when it hits the axis is not an important value that we care about. All right. So revenue is a curve, right? So you can see that if you increase the price, the demand goes down. Right? You see how the demand is going down. Right? So the price is getting higher from 5 to 9, but the demand is going down, and then the revenue is going up, and then you reach this critical value right here. That was right in the middle, which was $7. That's our best price. That's our optimal price. Let's see if I can put a star around it. $7, that's the worst star ever. Why am I trying? Why, Dr. J? Why do you do this to yourself? All right, so that's our star right there. $7 is the magic price. Yeah, and you can see very clearly, or you can look at your previous thing right here. The revenue, $7. The quantity was 42. 7 times 42 is $294. Again, the graph is not to scale. So $294 is the max revenue. That's our max revenue. So, again, let me draw my arrows going this way. Increase price, decrease demand, increase revenue. This one, so I'm going to draw both the arrows going towards the optimal point. Here, I'll get rid of that arrow because it's confusing. Here, we are going to decrease the price. We're going to increase the demand. The demand will go up, and then we are also going to increase revenue. Your goal is always to increase revenue. You always want to increase the revenue. I mean, if you want to make any money. If you don't care about making money, then give it away. Give it away now. All right? Well, there you go. I wish I could just say lecture done, right? Maybe in the old days I would say that, right? If this was the 90s, I would say, okay, that was your lecture. Now go read the book, do your homework, and see you in class on Monday. But this is the 21st century. This is the age of technology and the age of YouTube. So I'm going to do some more examples here. All right. So let's do some actual problems from the homework other than vocabulary. So far, I've just given you the vocabulary. Let's see. Given. So now I'm going to give you an actual function. Demand function. This one is not a straight line. That would be too easy. So 275 minus 2p squared. That's our demand function as a function of price. Find the elasticity. Elasticity when the price is $9. I don't know why $9. I just made it up. Just picked a price. Okay. All right, so let's go ahead and do it. So first, find the derivative. D Q dp. I sometimes get those upside down because my Q's and my P's. Mind your P's and Q's. Good lesson to learn today. All right, remember, that's just the same as x prime of P, all right, using the derivative. This is the other notation for the derivative. It's pretty straightforward here. It's just going to be negative 4P. All right. Yeah, just using the power rule, and the derivative of the 275 becomes 0. So then we have our elasticity. We'll put that in there, negative 4P times P over Q. Right. We have P. So P is 9. All right, we need Q. Right. Q is just the output quantity. All right, so the output quantity is Q. So we got Q is, I'm just doing a little scratch work here. Q is 275 minus 2 times 9 squared. 275 minus 2 times 81. 275 minus 162. I don't want to be wrong, so I won't use mental math. 113. I probably could have done that without a calculator. So I'm going to plug in these values here. So I've got negative 4 times 9 times 9 over 113. Remember, there's an invisible 1 down here if that helps you from making an arithmetic error. So I've got 36 times 9. Or you could do 81 times 4. So that's negative 324, although, as I mentioned before, the negative doesn't matter. Divided by 113, negative 2867. So I'm going to take the absolute value, which will be 2.87. So that's our E. All right. Ignore the negative because it's an absolute value. There we go. Not too bad, huh? The only calculus you had to do was this step right here. Taking the demand function and finding its derivative. And then setting up the ratio correctly. I have screwed this up before. And I do this all the time. And I get it upside down or something. You're like, why is this not working? All right, so this is called elastic. So we say demand is elastic. And what should we do? We should lower the price. Yeah. That will increase demand. And that will also increase revenue. That's supposed to be a dollar sign. All right, so that's a pretty straightforward example. Yeah, they get worse. So if you're hoping for worse, they get worse. Sort of get the ball rolling here. I'm not going to draw any graphs for this one. All right? Just imagine the curve. If you imagine the curve, we're on this side of the curve. Yeah. So elastic is like you're on the right side of the revenue curve. Yeah. Inelastic is like being on the left side of the revenue curve, and then unitary would be right down the middle, right down the axis of symmetry of the revenue curve. I also won't draw the demand curve, but so this is revenue. I always say I'm not going to do something. I'm pretty bad at this, and then I do it anyway. This looks like an upside down parabola like this. So that's the demand curve. It's not a straight line. I call this falling like a rock. Yeah. Demand is falling like a rock, which means it's pretty sensitive to price. So the slope gets very, very steep, right? Very, very quickly. As the price gets higher, the slope gets much, much steeper, right? This derivative, and then you would end up, losing demand very quickly. So your sweet spot, which we'll find later in this lecture, is a little bit closer to a lower price. It's closer to the axis there. All right, but anyway, that's just an optional if you like to think about what the curve actually looks like. I know it helps me to visualize what's going on. Okay, example 2. We have a demand curve that looks like this. Is there a theme here with the 250? Oh no, the last one was 275. Okay. In the last one, the constant 275 didn't really matter. In this one, it will. This is a reciprocal function. All right, so let's find the elasticity at a price of $67. Much more expensive item here, $67. I do all of these examples in the abstract, so this is just a widget. Yeah, it's just some object, some item that your company is selling. We do sort of have a monotone product here. We're only selling one product. You could diversify. That's something for an advanced class or a business specific class, which I don't teach. I just teach you the math. In other classes, economics and business, they'll teach you more about diversification and having other products to choose from. Just watch Shark Tank if you're curious about how that works. You want to get the easy version. I'm going to give you the Dr. Jordan Mathematics Calculus version. So we start off with our derivative, dq dp. So that's our E, and then P over Q. One way to remember this, if you don't have notes or something, the Q's should always be, sort of opposite sides of the fractions, and the P's as well. Because remember, your goal is that they sort of cancel out and you get one. It doesn't always happen, but that's the ideal, the optimal. Go ahead and find the derivative. So x prime of P, a little scratch work over here. Oh, maybe this will help you. I don't know if I always do this, but I like to rewrite this as 250 P to the negative 1. And then when I do the derivative, the power rule is very easy. It's negative 250 P to the negative 2. That's our power rule for reciprocal functions. Or you could say dq dp, again, tomato, tomato, these mean the same thing, negative 250 over P squared. So that is going to go right in here. All right, we're going to need to know the price, and we're going to need to know the quantity. We have the price, so there's our P. We're going to need to know the quantity, so we just use this function. I regret choosing the price of $67 because we're going to have to round. 3.73134328, blah, 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 or approximately 4 units. All right. Now, don't do this yet. All right. It screws up your answer if you round it now. Now, you're like, well, why did you do it then? You just told me not to do it. Well, because I want to tell you what the quantity is, right? The quantity is 3.7 units. Now, we could get into a philosophical debate about whether or not 0.7 should be rounded up or down. I mean, there is that 5 or greater rule. So 7 is greater than 5. So if that wins the debate, then you would say 4. But there's another side of the argument that, well, if you go to 4 units, you're not actually at the right number, because the right number was 3.7, right? So I'm not going to go there. If you do not get a whole number, keep this for now. All right, we can always round it later if the time comes. So we're going to plug that in there for Q. One other thing I'm going to do here is simplify the P's. So I've got negative 250 over PQ. I don't have enough room to do that, so I'm just going to put it in now. It's 1P and 1Q. You got that in your notes. The P is 67, and the Q is 250 over 67. And this is why I wanted you to keep it unsimplified, because I knew this was going to happen. If you would have rounded it to 4 units, then that wouldn't have happened. These 67s would not have canceled out. So you're going to get the absolute value of negative 250 over 250, which is equal to the absolute value of negative 1. And so E is equal to 1. Right, there's your unit elasticity, or simply unit elastic. All right. So again, on the revenue curve, that means that we are right here, max revenue. Revenue is already maximized. Okay. So keep the price unchanged. $67 is the perfect price. There's our p-axis. And if you're curious about what the demand curve looks like, again, it's not a line. Q is like the Y and P is like the X. It's kind of like this. It's a reciprocal function, which is interesting. With a reciprocal function, if you have a chance to play around with different values of P, if you're actually doing a project or doing an analysis or something in a business setting, and you do some price checking where you try different prices. At the beginning here, for low prices, when the price is very small, the demand drops drastically, right? So it drops like a stone. But then over here, when you raise the price, suppose you're already, so we're somewhere like right around here, right? So this is the E equals 1. It's not exactly in the middle, but it's somewhere on the curve, right? If you raise the price, the demand is not going to change very much. All right. Anyway, you don't have to draw any of these graphs, but if it's helpful to you to think about demand and revenue are separate graphs. If you try to draw them on top of each other, it gets really messy. So I just think of them as two separate sides of the coin, heads and tails of the same coin. All right, well, let's keep rolling. I don't hear any questions from the internet, but if you have them, post them. Email me. Post your comments on YouTube. I appreciate your feedback. So this one is a square root demand. So 125 minus 2p under the radical. Find the elasticity when the price is $36. You draw a dollar sign with 1 or 2 vertical lines? I don't care. I do it both ways. Okay, a quick review. First, for square roots, if it's been a while since you did this, hopefully it hasn't been too long because this is done in one of the previous lectures. A square root is a 1/2 power. And we just learned the chain rule. So you're going to take the power rule first. That subtracting 1 from the 1/2 gives you a power of -1/2. But then remember the chain rule, which we just learned. Then you take the derivative of the inside, which is -2. So your dq dp is -2 over 2 times the square root of 125 minus 2p. And you can divide the 2's out, or also known as canceling, and you get -1 over the square root of 125 minus 2p. So that's your dq dp. And then this is your p. How about in this one, I get everything all set up. What's the q going to be? It'll be the square root of 125 minus 72. Right? I'm moving along a little quicker now. I'm just plugging in 36 for p, and that'll make that 72. Again, we might not get a whole number. So 125 minus 72, 53. All right. Now, just for curiosity's sake, I will do the square root. It's 7.2, so that's approximately 7. Right? Again, using the rule of rounding. However, if you plug 7 into the elasticity formula, your answer will be slightly off. All right. So, in your capitalism, world, when you're thinking about the products on the shelf, sure. Yeah, you could say it's 7 units, 7 items, right? But in your calculus world, which is separate from the material world, it's not 7 units, it's the square root of 53 units. That's what we're going to plug in for our Q. All right. So I've got my dq dp, that's going to go here. Oh, I should plug the p into here as well. Notice that that's the same expression, 125 minus 72. So that's just going to be the square root of 53 again. I'm saving myself a little bit of whiteboard because I'm getting nervous. I'm getting towards the end. All right. And then I've got my P goes on top. And my Q goes on the bottom. And this is why you don't want to round it. I mean, sometimes you get lucky and it's, the square root of 25 or the square root of 49 or something. I mean, if that happens, that's fine. Then go ahead and do it. But if you get some non-perfect square, keep it as a non-perfect square and let the mathematics do its thing. Let it work out its kinks, as it goes along. So you're going to get negative 36. This negative is with the 1 there, negative 36. But again, you hear me say this a lot. It doesn't matter. It's going to be positive anyway. And then the square root of 53 times the square root of 53 is just 53. Right? Although you could do this. I have seen people do this. They'll go 53 times 53, and you get 2,809, and then you hit the square root button and you go, oh yeah, of course it is. Right? Square root of 53 times the square root of 53 is just 53. And then let's divide that by 36 and get rid of the negative. So we get 0.68. That's our E. 679, so just 2 decimals is sufficient. So this is inelastic. So what should we do? Again, if it helps to draw the picture, draw the picture. Inelastic means that the price is too low. So you should raise the price. Decrease demand. This is the weird part. You're intentionally decreasing the demand, right? You're saying, okay, as a supplier or as the producer, I would rather have less people buy this product at a higher price, and that will increase revenue. Right? So there you go. If you like to see the pictures, revenue looks like this. All right. We had a price of, what was it, $36. So we were on the left side of the curve. And so what we wanted to do was raise the price, right? Something bigger than 36, and then that'll get us up to the maximum revenue. I think we'll do that next. We'll figure out what this magic price is, the optimal price to get the maximum. So that's how revenue works. For demand, now this is an interesting graph for demand. It looks like this. Again, I'm not spending a lot of time on the graphs. It's just I understand the shape of it because of the square root and the negative. It's only quadrant 1, And so again, we're at a price of 36. We have E equals 0.68. That's less than 1. So it's inelastic because E is less than 1. So what are we going to do? We're going to raise the price, right? The demand is going to go down a bit, right? It's not going to go down by much, though. It's only going to go down by less than 1%. So for every penny on the dollar, so this is a $36 item. Oh, it's a tough one to do, $36. So a penny would be, oh God, my brain hurts. 36 cents. Yeah. So if I raised it by 36 cents, right, then the demand would go down by 0.68%, right, which is less than 1%. So the demand does not go down substantially, but it is. See, it's a very slow decrease in demand. And again, our goal would be to find the sweet spot here where the E is equal to 1. And I think that's our next example. I think I've gotten to the point. Yay, we got there. So in our next example, I'm going to try to find this point exactly. Right? I know that I need to raise the price, and I know that I will lose some demand, so I'll have less customers. But overall, I will increase the revenue, and we'll end up making more money, right? Which is the goal. It's better to sell less if the result is that you make more. Okay, well, we're rolling right along. It's been an hour, but we're making good progress. We're really getting into the heart of it now, and the heart of it is to find this point called unit elasticity, or the quick way to say it is unitary. We want to find P. I'm going to use a simpler example, though. Not that this one is hard. I don't want you to, there's nothing terribly difficult about this, but I prefer just to do an easier example. So, example 4. I'm going to go right back to where we started in the introduction with a linear demand function. This is by far the easiest to analyze. It is the most common. It's just a straight line, decreasing line. So calculate the elasticity of demand. I could also just say find elasticity, fancy way to say it, at a price of $5. So it's a cheap item, $5. All right, so let's do all of our prep work. dq dp is just x prime of p, which is just -8. Yeah, it's a straight line, negative slope, done. Right, could have done that in basic algebra. So p, q, straight line. Yeah, slope is -8. That's nice. It doesn't get any easier than that. Let's say slope. Slope. -8. All right, and then let's do, we got our P, so let's do our Q. Q is just the output of the demand function, so -8 times 5 plus 116. My confidence is shot from making mistakes. 76. If I make mistakes, I'd rather make them in private, where you can't all watch me screw up something. Occasionally I get an email about a mistake I made. I'm like, oh well, I was being recorded, so of course. So the elasticity, when in doubt, calculate. I got my dq dp, so that's -8, technically -8 over 1, and then I've got my P, which is $5, and I've got my Q, which is $76. So my elasticity is -40 over 76, absolute value of that. And ignore the negative, you're going to get 0.53, if I calculated that correctly. All right, so this is inelastic. Inelastic, it's less than 1. So we're right about here. $5. The quantity was 76. It's a lot like the first example I did. I mean, the numbers are a little different, but it's the same concept. And what we want to find is this point here, where E is equal to 1. So here we have E equals 0.56. So we're on the left side of the perfect optimal price, and our goal is to find this price here. We know we have to raise the price. It's going to be more than $5, which is the whole point of calculating the elasticity to begin with. Right? Find the elasticity, and then that'll tell you whether you're going to lower the price or raise the price. We know we have to raise the price. It's got to be more than $5. So what is the best price? What price would result in unit elasticity? Well, I don't know. Right? That's why this is a math class, right? We propose questions and then we solve them. Right? So what we're going to do is we're going to calculate E as a function of P, and we're going to leave it as a variable. We're not going to plug in a P yet. So we still have our derivative. Our derivative is -8, or -8 over 1, down 8 over 1. Yeah, that's the slope. But instead of plugging in a value for P, we will just leave P as a variable, and then we will represent Q with the expression negative 8P plus 116. All right, and then we want this to be 1. So we're going to solve for P. Now, we have the absolute value. All right. Now, I teach this a lot in my algebra class. The result of an absolute value, right? The output is always positive. But if the input is negative, then in order to make it positive, you remove the absolute values and then you multiply the whole expression by negative 1. So the absolute value of a negative number, and this number is negative, right? If you don't believe me, remove the absolute value bars and calculate it. Spam. If you calculate this value, you get a negative number every single time, right? And then your absolute value turns it positive. I hope you've caught on to that in the last few examples. Right. The only reason why we have the bars, absolute value, is just to turn that negative positive. So we just remove this, right? Remove the bars, multiply by negative 1, and then now the absolute value bars are gone. So now we have, and by the way, when you multiply by negative 1, just multiply the top. Don't do the top and the bottom. I don't know how long it's been since you had algebra, but multiplying a fraction by negative 1, you want to multiply the top, the numerator, by negative 1. Now, if you're a real fan of the algebraic method, you might say, well, could I multiply? You might challenge me on that. You could multiply the bottom by negative 1 and then not multiply the top. That would be fine. But then you'd have to remember, if you choose to do the bottom, then you have to leave the top as negative. Then you would change the bottom to a positive. But then you would also have to remember to change that 116 to a negative, which is where most algebra students screw up. Right? They change the wrong thing, or they forget one of the terms. So I recommend to keep your algebra mistakes minimal by just doing the way I do it, which is multiply the top. Boom, you get a much easier answer. Okay. And then another cool fun fact from arithmetic is that a fraction is equal to 1 if the numerator is equal to the denominator. You can also think of this as multiplying both sides, or some people call it cross-multiplying. I like to just use the fact of unit ratios. That's what this is called. A unit ratio is a ratio that's equal to 1. Every unit ratio in the entire universe, if you have a ratio that's equal to 1, the numerator is equal to the denominator, no matter what context, no matter what type of problem you have. So now I have 8p equals negative 8p plus 116. And this is the easy part. I call this walking the dog. Just take the dog for a walk. My dog named Algebra. Divide both sides by 16. And I get my optimal price. If I was brave, I would just do that by hand, but I'm not going to. I want to be right. Oh, I love this when this happens. No rounding required. $7.25. So that is the optimal price. $7.25. And then my elasticity would exactly be 1. Yay. This will maximize the revenue. This price will result in a max revenue. What is that revenue? I haven't done that yet. I've drawn these sort of abstract curves. What is that revenue? You know, what is that max? That is the worst parabola ever. Sorry about that. How about this? I don't know if that's any better. What is that revenue? Well, it's pretty simple. R is just PQ. So the easiest form of the revenue formula I've ever given you. It means that you're multiplying P times Q. So, I mean, we will see, or if we haven't already seen, more complicated, you've already seen it, more complicated formulas for revenue. This is a very simple one, right? So the revenue is $7.25. I'm going to use parentheses. That's my P. And then my Q is right here. -8 times 725 plus 116. So that's -58 plus 116 is +58. Now, I don't know what these things are, but this is the revenue for selling the 58 of these particular items. $420.50. That's our revenue. Or you can just say 420.5. There's no need to round when it's money, unless you get more than 2 decimals. If you get more than 2 decimals, as I've always done in a business setting, I round it to the nearest cent. So 0.5, 50 cents, whatever, same thing. One thing I don't really talk about in this lecture is the time frame. So is this $420 a day? Is it $420? I hope it's a day. Is it $420 a week? Is it $420 a month? God, I hope it's not $420 a year. I'd be going out of business, right? Hopefully it's a day. That would be great. Time comes into play when we start introducing T. I did a little bit of that in the previous section. We may do more of it in the future. We put a variable for time and we say, you know, every month or every week or every year. I'm not going to do that today. So everything is sort of math in a bubble, in a vacuum, just in the abstract sense. I might also do some examples where the product is more well-defined, you know, what we're actually selling. Although oftentimes when I do that, I just make up a product name. It's not, it's irrelevant to the process. All right, we're almost done. You hanging in there? All right, example 5. Example 5 is my favorite type of word problem. And I actually give this problem to my algebra students that don't know calculus yet. Because this problem really doesn't require any calculus. But if you've never done it before, it can be tricky. Suppose an item... The price of an item, sorry, suppose the price of an item increases from $26 to $28. So a $2 increase. I don't really worry about the percentage of what that represents. If you're curious, you could do a $2 increase and calculate the percent. It's more than 1%. And the demand decreases from 780 to 672 units. So this is kind of real world, right? I'm selling these products. I raise the price to sort of test the market. And then at the end of the day, I always like to think of it as a day. At the end of the day or the end of the week or whenever, I tabulate how many I've sold, and I found out that I sold less, right? Which is pretty common, right? If you raise the price, you're going to sell less, all right? But you were bringing in more dollars per item, so that could be well. Find the elasticity back when the price was $26. All right. So we've got dq dp over p times q. Now, the only difference, I mentioned that I teach this in my algebra class. I teach a milder version of this problem. We don't say dq dp, we just say slope. Right? In an algebra class, we don't call it the derivative, we just call it the slope. Now, we got to keep in mind, the slope is the change in quantity over the change in price. Right? You got to make sure. It's really easy to remember it when it's y and x. Yeah, y goes on the numerator, x goes on the denominator. It's easier to screw up when it's p's and q's. Right? So mind your p's and q's. P is like x and q is like y. All right, so the quantity goes in the numerator. So 780 minus 672. So my change in quantity, I'm going to feel silly as soon as I do this. If you're watching the video, you're like, it's 108, Dr. J. I just wanted to make sure. I'd rather be right. All right, and then my change in price, I don't even need to do the math for that. That's negative $2. Actually, no. The change in price is positive $2. The change in quantity is negative 108. I actually did that backwards. There we go. I fixed it. I want my calculation to match the phrasing of the problem. So the demand decreased, so negative 108, that's Q, and the price increased by $2. I could have written that out, 28 minus 26, but I hope it's clear that it's $2. All right. So this is just slope, negative 108 over positive 2. I could just say 2. That's my slope. Times, and then I'm going back to when the price was $26. So the price is 26. The demand was 780. And notice I really didn't do any calculus. I just did some algebra. And that is fine. You could simplify all of this, spend 5 minutes doing that if you want. I'm not going to. I'm just going to multiply 108 times 26. It's all going to work out in the end. 2,808. And then I'm going to multiply 2 times 780. 1,560. And then I'm going to divide them. Oh, shoot. I'm glad I paused for a second. 108 times 26. 108 times 26. Oh, no, I had it right. 2,808. I had read my screen and thought that there was a 4 in there somewhere. There's no 4, right? Everybody agree there's no 4. And then divide that, divided by 1,560. And get rid of the negative, 1.8. So demand is elastic. we should decrease the price, increase demand, increase revenue. All right, 1.8 is too high. Yeah, it's greater than 1. So the price of $26 is too high. Well, we're doing it, right? We're doing it. Let's find that price. Decrease the price to what? What should we do? Well, this is a little trickier now. This gets a little trickier because in order to do this, to find the price, I'm going to write this down because I'm about to erase it. Find the price such that E of that price is equal to 1. So we want unitary or unit elasticity. Well, we have the slope. The slope is negative 108 over 2, which is negative 54. So that's our slope. That's our M. So we need a line Q equals MP plus B. Remember, Q is like Y, P is like X, M is negative 54. Now, there are lots of fancy ways to do this. You could draw a graph, make it very nice and straight, and then find the B that way. You could use one of the fancier formulas, y2 minus y1 equals mx2 minus x1. I'm just going to kind of do it the simple way, what I think is the simple way. Pick one of these prices. It doesn't really matter which. I'm going to go ahead and take the second one, and I'm going to plug it in, 672 for Q, and 28 for P. And this will tell me what B is. So what do we got? 54 times 28. Is negative 1512 plus B. And then I'm going to add 1512 to both sides. So much of this course is a review of algebra with a splash of calculus and a dash of business terminology. So I get 2184. All right. This is the demand at which the price is 0. Sometimes call it the giveaway demand. So if you were giving it away, the price was 0, you could give away 2,184. Although a lot of these models, when you think about reality, they don't exactly line up. Maybe I only have 2184 in the shop, right? So if I give it away, I'm going to give away all 2184. People are going to come take every single one of them. And then the slope is going to go down like this. Yeah. And our goal is to find when E is equal to 1, we want to find P. What price is that perfect sweet spot that I talked about in the introduction? All right. So now I have a demand function. X of P is equal to Q. Or I could say Q is equal to negative 54P plus 2184. these mean the same thing. This is the function notation. This is just the standard linear line notation. These mean the same. All right. And then my slope M is negative 54. That's my dq dp. Okay. So now I'm ready to solve for P. So I've got absolute value of negative 54. That's from the elasticity formula. Times P. P is an unknown. And then divided by Q. Negative 54P plus 2184. So everybody goes in the pot. And then set that equal to 1. Hey, wait a minute. I feel like we've done this before. Multiply by negative 1. Remove the absolute value bars. You're going to get 54p equals, numerator is going to equal the denominator. If you do this once or twice, you're going to notice a distinct pattern in the procedure. All right, there it is. The last time I think it was 8 and 8, or 8 and negative 8, and then it became 16. This time you're going to move the 54 over. Can I save some space and just say 108? I hear a big yes on the internet. Yay! Right? I'm adding 54 to the other side. I'm already approaching my hour-and-a-half mark, and I still have one more example to go. All right, now divide by 108. And there it is. There's our sweet spot. 2184 divided by 108. $20.22. It's 222222222. We're going to round that to $20.22. Well, I want to do one more that's not a line. All right, and then that'll be the end of it. So the last example. Now, when you do your homework, or I don't know what you're watching these videos for, but if you're in my class and you're doing your homework, if you're just watching this for fun, then I hope you've enjoyed the show. I'll be back with another video soon. If you're doing this for credit and you're going to do the homework, this last example, there are 2 of these, and I'm going to show you how to do one of them, and you can figure out the other one on your own, because I'm already reaching my limit here. But I want to show you an example that's identical to the one that we just did in the question, but the form of the demand function is a little more complicated. This one has a combination of a square root and a square. I'm not going to get into the weeds on the graph, all right? It's sort of like a curved edge of a ellipse, which is kind of a stretched out circle, if you really wanted to put it into Desmos or something to see what the graph looks like. All right, but I'm not going to get into that. I'm just going to do the math. And I'm going to ask you exactly what you need to know, which is to find P such that E of P is equal to 1. I'm not going to do the rest of the questions that I've been doing. You can do that yourself. If I give you a price, I think I've already exhausted that process, right? If I give you a price, you just plug it all in and tell me what the elasticity is. That's the easy part. This is the harder part. And so since I only have a few minutes left, I'm going to try to just take care of this last part. So we got a lot of work to do. We got the derivative, x prime of p. That's going to be 1 over 2. You should probably just memorize this for square roots. It's always 1 over 2 times the square root, leaving it untouched. So don't do anything to the square root first. Leave it exactly the same radicand. Then use the chain rule, multiply by the derivative of the radicand, or the inside of the radical. You might notice that you'll end up with this over 2, and then you'll end up with this 2 here. So that'll become negative 0.01 again. That's very common. That goes right back to being that. But then you've got this extra p here. And then you've got your square root 450 minus 0.01 p squared. So that's just your derivative, dq dp. All right. Now let's find the elasticity. EP as a function of p. So it's going to be this derivative. Times another p over q, but remember q is just the original function, which I erased, but we still have it. It's right here. It's the original function. And then what we're going to do is set this equal to 1 and find p. So negative 0.01 p squared. We're going to multiply the p and the p. And then square root times the square root. Hey, this looks very familiar, right? We've done this before, but these were numbers, right, instead of expressions. The same concept applies. The square root of an expression times the square root of the same expression is just that expression. And then we're going to set it equal to 1. All right, so now we're going to remove and multiply by negative 1. Multiply the top by negative 1. All right. In the interest of time, let's do some video magic. Sorry. Here we go. Some video magic. When I remove this, there's a negative. I'm multiplying it by negative 1, and by the magic of whiteboards and erasers and video technology, that is the expression that you get for EP. So this is just EP. This is the elasticity as a function of P. All right. And now I'm going to set it equal to 1. As was mentioned several times in this video, if a ratio or a fraction is equal to 1, that just means the numerator is equal to the denominator. Then you can move the p squared to the other side. I'm running out of space here. So I get 0.02 p squared. Oh, it's back, right? It's 0.01, 1/100th plus another 1/100th, p squared, and then 450. So p squared is 450 over 2/100ths. 450 divided by 0.02. 22500. If I planned this problem right, P is the square root of 22,500. Come on. Yeah! I love when that happens. We get a nice whole number. And I hope that happens to you when you do this problem as well. Whew. I know I went over a few minutes. The bell has already rung. Thanks for hanging out with me, folks. That's it for Elasticity of Demand. Until we meet again, I'm Dr. Jordan, and I'll see you on the internet.